Large is for tournament because it begins very early. When the number of vertices is larger than 50, it begins to be large for a tournament, and we want to deal with very large, around 1,000 vertices, and so it's for large tournament. But the problem is very present when the number of vertices is small. And the median linear problem is coming. It is a decision problem in which you have a set of item, X, and a set of expert, N item and M expert, and you have a profile of linear orders, there are permutations on X, and so you have a set of permutations, and you want to compute a linear order, which is a consensus order, to represent this opinion and to summarize them. It's a very classical problem in social choice theory or voting theory, because the vote can be expressed as a preference order, as a permutation, but also for preference aggregation, when you have to rank some products or some methods, algorithm, for instance, you can compare them with many criteria and have to choose which is the best algorithm for any problem, or you have to rank students, or at the end we will see, as they do in Shanghai, you can rank universities. So I refer to my colleague and friends Jean-Pierre Barthélémy and Bernard Monjardet, who talk about the median procedure in cluster analysis and social choice theory. And they learned me finally that an order relation is a relation on pair on X elements. Because when you take two of them, X is before or after Y, and so order relation are considered as set of oriented pairs. And median element needs to be computed with a distance, and the distance used is a Kendall distance, the symmetrical difference between two relations when you count the number of disagreement between the relation. That is the number of pairs for which X is before Y, and for S1, and for S2, Y is before X, or conversely, Y is before X and X is before Y. And so it's the disagreement between these two relations. And what is the median linear order for the profile? It is a linear order such that the remoteness, which is the sum of the distances, the Kendall distances between this median order and the different permutation, is as small as possible. So how to compute such a median order? It's very classical. You have to build a table corresponding to pairs, and T of xy is the number of orders in the profiles such that X is before Y, and so T of xy and T of yx, the sum is equal to the number of experts M. And so with this table, you build a tournament in which you have an arc between X and Y if T of xy is larger than T of yx. And this tournament can be weighted with the difference of the two values. And in that case, the complementary value is equal to 0, or it can be unweighted. And in that case, if y of xy is positive, then you transform it in number 1. So the tournament is not weighted. And so it is very clear that a transitive tournament corresponds to a linear order. And otherwise, the problem is to compute a median order. And the solution is to eliminate the cycle you have in the tournament, reversing some arcs. And the problem, which is called the Kemeny problem in case of weighted tournament, is to minimize the weight sum of the reversed arc to make the tournament transitive. So you have a tournament, and you want to reverse some arcs to make it transitive, and you are looking for the set of arcs for which the weight sum is minimum. A small example, you have a profile with 6 linear orders on 4 elements. When you count 1 is before 2, 1 time, 2 times, 3 times, 4 times, and 2 is before 1, 1 time and 2 times. So the difference is 2, 4 minus 2, and the converse is 0. And you build the weighted tournament in that table. And it's clearly a transitive tournament since nobody is before 1, so 1 is the first. And when 1 is out, nobody is before 2, 2 is a second, and so on. So you have a transitive tournament for the natural order. So how to compute when the tournament is not transitive, how to compute a median order. And the solution is a very old one, which has been proposed since many years by myself between other persons. It's a branch and bound algorithm. And this branch and bound method has been improved by many people, beginning with Jean-Pierre Barthélémy, Olivier Udry, Irène Charon, and so French colleagues. And we progress on this topic, and I will speak of the new developments. So a branch and bound algorithm begins by establishing an upper bound for the remoteness of an order to the tournament. And so it is made by heuristic methods. You test some orders and you compute the remoteness, and finally you have the smallest one, which is an upper bound for the remoteness of an order to this tournament. And so after you build a tree as branch and bound method with the beginning section of order. An order can begin with 1 element, and after this one can have another one, and so on. And so from a leaf in this tree with minimum remoteness, you extend this beginning section, adding all the possible non-ranked elements if the remoteness of the section remains lower than the bound you first evaluate, and until to get a linear order. It's a simple algorithm which can be extended, but it is very hard to compute a solution when n is larger than 30, generally 50 if you have if the tournament is close to be transitive, so you can find a transitive order quickly, but if not, you can't. So I will not develop the branch and bound method because okay, so if you know it, it's clear, and if you don't, read it in the paper or any paper. Right. But if this is a table, which you can evaluate with, by chance, a good order. So I know that the solution is at remoteness no more than 4, and so I cannot begin with A because the sum of weight before A is 10. B, okay, you can begin with B. You cannot begin with C. We cannot begin with D. We can begin with F. And so you have in the branch and bound tree, you have 2 beginning positions. And so the one with the lowest cost is extended, and so it is out before, and you continue restricting your tournament because you test the possibility. So I don't detail this thing anymore. And so the problem is to have a very good upper bound for the tournament because you limit the extending of the branch and bound tree. And so many classical heuristics can be tested. I only refer here to deterministic ones, but there is also many probabilistic ones. And so the classical method is Borda scoring method. You sum the ranks of the items, and you take the order of the sum of the ranks, and so it's the proposed method by Borda during the French Revolution, before the French Revolution. So it's not that. You have a classical method also, which is called as a Smith and Payne. at what step you reverse an arc which is involved in the largest number of 3 cycles. Because in your tournament, you can consider only the 3 cycles because it's a complete, and so you have to reverse, when you have a 3 cycle, you have to reverse one of the arc, and you choose the arc which is involved in the largest number of cycles. You have a very simple heuristic, which is the increasing order of the half degree, internal half degrees, the number of vertices that dominates X, and so you choose the one which is less dominated, and it's a very good heuristic in the average for unweighted tournaments. And the greedy heuristic, which at each step you select an element for which the sum of the dominating weights is minimum, and you update the sum, and it is again the average best method for weighted tournaments. And so I will call best H the heuristic order at minimum remoteness of the tournament from these heuristics, or any you can add or test for that. And so I have it is after also a local optimization procedure. I will detail just a little because I think it's original. When you have an order, when you have an order, you can look for any element which is the smallest reversal arc from this element. And so, if OI is before OG, and this is a small arc, you don't have any arc between beginning on OG and finishing before OI. And so you can exchange OG and OI. It's very easy, but doing so, you gain something, the weight of this reversal arc, but you can, maybe you could introduce other reversal arcs, because here you have OI will be at the place of OG, and if you have a reversal arc between OI and OK, it will become a reversal arc. So you can, for the shortest reversal arc in any vertex, test if it will be convenient to exchange this one and the preceding one. So now all that is classical, and what is the idea? The idea is to decompose, to factorize the tournament, because the heuristics are good when the number of vertices is small, and they are loose when the number of vertices get larger. And so the idea is to decompose a large tournament in sub-tournament that will constitute a partition of the item set into clusters of elements which could be closed, which should be closed in a median order. And doing so, you can compute a median order or a good approximation, because the number of elements is smaller, and at the end, assemble them into a composed linear order. So this is the idea of a decomposition method. Okay, how to do that? The first thing is to test a balanced decomposition, because the best heuristic gives you an order, and you can slice it in P classes, you fix P, and the first items are in the first class, and the second on the second class, and so on. So you get a balanced decomposition. For each class, you compute the median order or a good approximation, and you continue. And the second idea is to make a partition based on distance. The distance is natural because for any element in X, you have the set of those that dominates that are dominated by for X, you have the set of elements that dominate X and the set of elements that are dominated by X. So it's X plus and X minus, these two sets, and you can count the symmetric difference distance between these two parts for X and Y, X plus, X minus, compared to y plus and y minus. And so you have a distance which is a sum of the different symmetrical distance between these two parts. Why is it a good distance? Because if you have a transitive tournament, this distance is proportional to the rank difference between x and y in the median order. So if the tournament is close to be transitive, so this distance will be put together, elements will be close in the order. So I have two methods, and I want to I have a metric, and I take a partitioning method from a metric to establish the class. It's a kind of Kamins. It has no much importance. And so you get a partition corresponding to this metric, and it is PM. So I want to understand if this is a good technique to improve the median linear order, the approximation of a median linear order. And so I will do some simulation protocols to test if it is efficient to make this decomposition, or if it is the same to take the heuristic as they are. And so I will select three kind of data. Random profile. Okay, I take m permutations, random permutation of on X with an element, and I establish the majority weighted tournament T. Okay, and I compare decomposition and not decomposition. I have another test with the problem with random permutation is the consensus has no meaning. So if you can obtain something, but you can obtain something which is not very close and which is okay. So I will take permutations for which these permutations are close together, and for that I start from the natural order 1 to n, and I make a small number of permutation. I make this m permutation transposing a small number of pairs in this natural order. So all the orders are close to the natural order, and so the consensus could be the natural order, because I make the transposition randomly. And the third test is with tournament with bounded remoteness, because with natural order I have a transitive tournament, I have an exchange pair symmetrically around the diagonal, and so I reverse arc, and so making T reversing arcs, I'm sure that the natural order is at a remoteness lower or equal T. I can do better to come back to the natural order, to an order, not necessarily the natural order, but I'm sure that the natural order is at most at remoteness lower or equal to T. And so that is the results. I take for n value from 100, 200, 500. The number of permutation, I make it vary to see. And the number of class I check can be constant, because for n equal 10 and so on. So the best heuristic is this column. This is the three first column are for unweighted tournament, and the three last are for weighted tournament. So for unweighted tournaments, okay, the best heuristic give me a remoteness to the tournament. By the decomposition, the balanced decomposition give better results at each time, and the computed decomposition also give better results. Not systematically, but always better than the best touch. And it is the same for weighted tournament. So mainly, it is a good idea to make this decomposition. What is the effect of the number of class? Because I don't know it, and I take just some value to see, and systematically I can look at for n equal 300 and 100 order. I can check the number of class I take for the decomposition, the balanced or the computed decomposition, and find which is the minimum. And I arrive to the conclusion that maybe good classes are around 30 elements. It's a little large to make a median order, but it can be checked also, see if you have time to. And so after I look at closed the set of closed permutation, and take n equals 300. The number of order varies. The number of transposition is small compared to the number of pairs, because, and so the number of classes is around 10, because I found it the best decomposition was around 30 elements per class, and the best heuristic is not so good. The balanced decomposition gives good result, but the computed decomposition is much better, and the natural order, which is suspected to be median, because I start from it and I just make free permutation. So sometimes it's better, sometimes it's not far from this solution. That's essential. And for unweighted tournament, it's always the same result. It is always efficient to make a decomposition, because it's much better than the best heuristic. And when in this time I know what is the remoteness of the natural order, so it can be very close, and so when the solution is when the computed order are very close to the solution. Okay, just to fun. I have tested on a real data problem of the Shanghai ranking. So I take there is in the Shanghai ranking you have 6 criteria with weights 1, 2, 2, 2. So it's as we have 10, and you have 500 universities that are evaluated, and a scoring function which is not very clear on the Shanghai site, but they finally give an order of their ranking. So they have something like a border scoring method, and they rank the universities according to this score. So I kept the same data with the same weight. So it's the same data, and I take only 150 university, thanks to Denis and so on. And it is 2010 a year, because I don't have the data for a bit later. And so, and naturally, it's a weighted tournament, because I count the number of times, the number of criteria, weighted, the number of criteria for which one university is better than another one. Okay? And so, what is the question? The global heuristic gives me a remoteness equal to 994. The ranking is the Shanghai ranking is far from this tournament. Okay, and the decomposition algorithm has been tested with some number of classes, and the computed decomposition gives me a remoteness equal to 864, which is much better than the global. So I conclude by the computed decomposition is better than the balanced decomposition, is better than the global heuristic, and is much better than Shanghai. And so, but as it is well known in voting theory and so on, the way you compute a winner, the winner depends on the method to compute it. And so, well, I don't insist on the thing. And so finally, the decomposition algorithm.
The slide you had before, this was the most interesting.
Oh, I hate it. So what are the difference between the Shanghai ranking and the median order of I'm not sure it's a median order. It's the best approximation I have of a median order from from the tournament corresponding to exactly the same data. So the MIT, which is 4, is exchanged with Stanford, which is 3rd. So the extent is, well, the 9th University Chicago is very well favored. It's it becomes 20th, and 5 universities gain at least 10 ranks, and 10 universities ranked after the 100 place become go in the 100 top. And so, and 10 universities lose at least 10 ranks, So there is some difference, and each university before the 100 place rank go to after. So, but that's how I say, the question is how to count. Shanghai decide how to count. But the problem for the university which fight to gain one place or one rank or two, or to become to be in the 100 top place, they should decide which are the good criteria for them and which is the good method to decide. That would be better than to try to gain one place, recruiting a PhD, recruiting a Nobel Prize, or asking to their teachers to make many publications in many and so, well, so finally, the idea of decomposition is efficient to the median order problem. Okay.